So stability in terms of time response analysis. This is the S plane, okay, and this is the right half of S plane having real part on the x-axis and imaginary part on the y-axis. So this is called imaginary axis, this is called real axis, and this whole plane is called S plane. Okay, now if we have poles and zeros on the poles on the right half of the S plane, then the system is unstable. As you can see that the response is growing. Response is continuously growing. If we are having a pole here, then corresponding to this response is growing. The pole here, then response is also growing. If we have a pole here, response is also growing. Now if we have poles at the imaginary axis, then the response is marginally stable because it is like this. The response is, it is not growing, but it is sustained oscillation. Sustained oscillation like this with constant amplitude. Either it is a constant value or it is a constant amplitude, not increasing in time. So it is BIBO, bounded input, bounded output, but the response is constant, either constant or oscillator. Now if we have poles and zeros in the left half of S plane, then the response decays down. The steady state response decays down to 0, and that is the desirable condition. That's it. That is what we want. Therefore the system is stable. So either the response is exponentially decaying like this, then the response is stable. Okay, so this is graphical representation of stable, unstable, and marginally stable system. So you can draw this diagram in your notebook. This is a very important, very good diagram. So I want you to note it down in your notebook. Take a numerical example and try to understand in a better way. Suppose this is your system with Rs equal to unit step 1 by S, and transfer function is given by 3 upon S into S plus 1 into S plus 2, and unity, it is a unity feedback system. Okay, so if you plot the pole 0, because this is the transfer function, open loop transfer function, then the closed loop transfer function will be 1 upon gs upon 1 plus gs hs is 1, so gs upon 1 plus gs. So if you try to find out the closed loop poles, then you will see that there are two poles on the two complex conjugate poles, that is j 1.047 minus j 1.047 and a pole with negative sign minus 2.672. So if we are having poles on the left half of the S plane only, the system response, if you try to plot, then the system response will be like this, a standard second order system response, which decays down to the steady state value, which is equal to 1, right? So this is a stable system. Now if we change the transfer function to be 7 upon S into S plus 1 into S plus 2, then if you try to find out the closed loop poles, then it will be minus 3.087. So this lies on the left half of the S plane. So this pole is fine, but we are having a complex conjugate pole pair on the right half of S plane, that is j equal to 1.505 minus j equal to minus j 1.505. So if we are having complex conjugate poles on the right half of the S plane, then the system is unstable system, and the response, time response of such a system will grow exponentially, and it will be oscillatory also, right? So such a system is an example of unstable system. I want you to note down this diagram, this example, for better understanding. Roll number 1. another example. So it is not a simple matter to determine if a feedback control system is stable. A typical example is that shown below, for which only the pose of the forward transfer functions are known. We do not know the pose of the equivalent closed loop transfer function without forcing or otherwise solving for the roots, which is a tedious task without using a computer program or some handheld computers. Okay, so suppose we are having a higher order system like s to the power 5 plus 28 s to the power 4. So if you want to find out the pose of such a system, then that becomes very difficult task, because you need to solve a fifth order equation, and that is not possible by hand calculation, huh? So such higher order systems, we need some other methods for testing the stability, and this method to test the stability without having to solve for the roots of the characteristic polynomial is called the Ruth-Herwitz criteria for stability. Okay, so what is this? So this method tells us how many closed loop system poles are in the left half plane, in the right half plane, or on the j omega axis without giving their coordinates, that is their exact locations. So method requires two steps: generate a table and interpret it to conclude about stability. So suppose we are having a system like this, having input as rs, output is cs, and the transfer function is some numerator, and the denominator is like this. So we are more concerned about the denominator of the closed loop system. So we just leave the numerator part and we focus on the denominator part, and we form a table. So a table having s terms. So s, since the highest order of s is s4, therefore we are starting from s to the power 4, then decreasing the order. So s to the power 4, s cube, s square, s, and s to the power 0. And what we take, we take the coefficient of s to the power 4 and write it here, and then we skip the odd coefficients, then we go for the even coefficient again, then that is a2, we put it here, then we skip the odd coefficient and we go to the even coefficient a0. Okay, then s cube, the coefficient of s cube is a3, so we substitute a3 here, and then we ignore the even part and we go to the odd part. The coefficient is a1, so we substitute a1 here, and next item is 0 because there's no other item, so we substitute 0 here. Then what we do, we form the we calculate the next row of the Ruth column, Ruth table, Ruth-Herwitz table. So how we do that? We form a determinant having a4, a2, a3, and a1 with minus sign. So take determinant a4, a2, a3, and a1 divided by a3, which is the element just above this row, right? So we call it as b1. Okay, suppose we calculate this value and we call this as n1, b1, and then again what we do, we take the determinant of a2, a0, a3, and 0, because we are here, so we skip this. If a4, a0, a3, and 0, we skip this and we take the divide by a3. This remains same because this is the a3. This is actually an empirical formula. I want you to note it down, and then we will move forward. Okay. For Ruth criteria, and Ruth-Herwitz criteria for stability states that the number of poles of the characteristic polynomial that are in the right half plane is equal to the number of sign changes in the first column. So this is the first column. So how many sign changes are there? This is plus sign, so no sign change. From S4 to S3, no sign change. From S3 to S2, there is a sign change because from positive it has gone to negative. right? So it is one sign change, then same sign, same sign. So there is only one sign change. So one pole lies in the right half of the S plane. Okay, so such a system is unstable system. So let us take a numerical problem and try to solve the system using Ruth's table. Okay, so suppose this is the polynomial 1000 upon s cube plus 10s square plus 31s plus 1030. So try to form the Ruth table and then find out the stability of the system. So when you should start from s cube, then s square, s1, s to the power 0. The coefficient of s cube is 1, then coefficient of s is 31 and then 0. Then s square is 10 and then s is 1030 and then 0. So since we are having 10 common in both, so you can take 10 common and you can substitute it by 1 and 103. Then you can form the determinant like this. So try to um, find it out yourself and verify your answers. We take the determinant here. So what the value of this will be 103 minus 31. So it is minus 72 divided by this value. So it is minus 72. Here also you take this and this 10 and 10. So value is 0 because 1 into 2 0 and 0 into 1 is 0. And here again you take this and this and this. So here if you don't have this, then we assume it to be 0 value. So it is 1010. This again is 0. So now this s to the power 0 is basically this and this column. So 7 1, this whole, this determinant will take 1 103 minus 72 0. So if you solve this determinant and divide by this value, so this value will remain the same throughout the row, right? So here you if you solve this, you get 103, and here you will have 10 because this value, this value, this value, and this value. So 10720 divided by minus 72. This you can calculate. It comes out to be 0. And here again 10. This is the thing. Then it is 10. Then minus 72 and 0. Okay. So this is how we form the Ruth table, and then we see how many sign changes. So there is one sign change, and then again one sign change. So a row can be multiplied by positive constant without altering the stability conclusion, because you can take 10 common. The system has two sign changes in the first column. Thus, the system is unstable since two poles exist in the right half of the S plane. Okay. And the remaining third pole is in the left half plane. All right. Then there are certain special cases. You can solve this problem, and I have given you the solution. Okay, try it out yourself. We are having such a system in which the value of first column becomes 0. So if we have this system, 2s to the power 5 plus 3s4 plus 2s cube plus 3s square plus 2s plus 1. So if you form the root table, then you see that this is 2 2 2 2 2 and then 3 3 1. You can form the root table, and when you, since these two elements are same, therefore this element will be 0, right? So what to do when one element of the uh, first column becomes 0? What we do, we substitute it with, we simply replace the 0 with a small quantity epsilon, supposed to be positive, and continue the table. Suppose we are taking, in place of 0, we are taking a very small value which is equal to epsilon, and which is non-zero and which is also positive, right? So if you do this and then proceed with the table formulation, then you will get this type of values. So you can check it out yourself. Then there are two signs. We can see that, so we can take the limiting value. You can take the limit of this and then limit of this, and the limiting value gives the actual value of the system. So there are two sign changes in the first column and the system in unstable, with two poles existing in the right half of the S plane, and the remaining third pole lies in the left half of the plane. Again, try to solve this problem with the help of Ruth criteria. Suppose you are asked to find out the stability of this system. So try it out yourself. Form the root table. Got the solution? This is the solution for the problem. You can cross verify your answers. Okay. So this is how we form the root table, right? And here again we are having 0 value in the first column, and then all the values are 0. This whole row becomes 0. A row of 0 appears in the s to the power 5 row. Thus the characteristic polynomial of the closed loop transfer function must have an even polynomial as a factor. So return to s to the power 6 row to form the even polynomial. So this is basically, if you return to this row, what you get is s to the power 6 plus 8 s4 plus 32 s square plus 64. Now differentiate this polynomial with respect to s to form the coefficients that will replace the 0 term at the s to the power 5 row. So dp by ds becomes 6s to the power 5 plus 32 s cube plus 64s plus 0. So from this value, you form this s5 column. So 6, 32, 64, you can take 3 common. So it is basically 2 common. So it is 3, 16, 32, and then last element is 0. So now you can continue with the procedure and form the rest of the rows of the root table. Okay, so this is how we form the root table if the complete row is having 0 in the root table. So we refer to the previous row and form that row, form the even polynomial, and then take the derivative and form the next row. Okay, so this is another special case, that is rows of zeros. This is how we solve such problems. Okay, now I'm giving you there are two sign changes from the even polynomial. Here two sign changes, because it is from plus to minus and then minus to plus. So two sign changes in the first column. So there are two sign changes from the even polynomial at s to the power 6 row down to the bottom of the table. Then the even polynomial has two right half plane poles. Because of symmetry about the origin, the even polynomial must have an equal number of left half plane poles. So this like this. The two remaining poles for the even polynomial must be on the j omega axis, like this, imaginary axis. There are no sign changes from the beginning of the table down to the even polynomial at s to the power 6 row. Therefore, the rest of the system characteristic polynomial has no right half plane poles. So the two poles in the right half plane is like this. So location is right half of the f plane, left half of the s plane, and j omega. So there are two poles on the right half of the plane, these two c, and then two poles on the left half of the s plane and two poles on the j omega axis. This is for the sixth order, then for second order, and then for eighth order. So like this, six from this, then second order from this, and then eighth order, like this. So you can note it down this first and then go forward. There are some important remarks about the Ruth Herwitz criteria. That is, a sufficient condition for instability is that the coefficients of the characteristic polynomial do not have the same sign, right? If powers of s are missing, the system is either unstable or at best marginally stable. And all the coefficients are positive and not missing, we do not have the definitive information about stability. Okay, a row of zeros in the root table means that the system characteristic polynomials have an even polynomial as a factor. Only j omega axis poles are possible when a row of zeros is present in the root table. A row of zeros means that the system is at best marginally stable. In case of root table with rows of zeros, we can always check the j omega axis pole by looking at the even polynomial. Okay, so I want you to note it down. This is very important conclusion. Do some more type of problems which we can solve with the help of Ruth Herwitz criteria. So find the range of k that will cause the system shown below to be stable, unstable, or marginally stable, and assume that k is greater than 0. So this is called stability design via Ruth Herwitz. So if this is the system k upon s into s plus 7 into s plus 11, then you can form the closed loop transfer function as k upon this whole upon into 1 plus 1. So this is the characteristic polynomial. From this characteristic polynomial, you form the root table like this. It is very easy. 1, 77, 18, and k. And then if you take this, multiply this by this, minus k upon 18, and this remains then k, because this value remains 0 because next item is 0. So this is 0, this is 0. So this whole multiplied by, divide by this, so it remains k. Okay. So this is how we form the truth table of such problems. Now, how to find the value of k? So since k is greater than 0, we see that all terms in the first column are always positive, right? Because here you have a k term. So if it is positive, then this is also positive, and this again is positive. Okay. Except at row s equal to 1. Here, if the value of this exceeds 1386, if it is 1387, then it is minus 1 by 18. So it becomes negative, right? So this term can be positive, negative, or 0 depending upon the value of k. So if k is less than 1386, all terms will be positive. And since there are no sign changes, the system will have 3 poles in the left half of the s plane and the system will be stable. Okay. And if k is greater than 1386, then s to the power 1 term is negative. Therefore, there are two sign changes indicating that the system has two right half of the s plane poles and one LHP pole, which makes the system unstable. Now, what happens when k becomes equal to 1386? Then we have an entire row of zeros. As you can see here, if this becomes same, then this becomes 0 and this again becomes 0. So this is the case of entire 0 row. So you have to form the even polynomial, that is you have to go above. So it is 18s square plus k. And k is 1386. So 18s square plus 1386 differentiated with respect to s, 36s plus 0. So substitute the value here, 36, and then replacing the zeros, row of zeros with coefficients of the last polynomial, we obtain the following Ruth table, right? Since there are no sign changes from the even polynomial down to the bottom of the system is stable. The even polynomial has two roots on the j omega. If you find the roots of this equation, then you can see that we are having two roots on the j omega axis which are purely imaginary. Since there is no sign change above the even polynomial, the remaining root is the in the left half of the S plane. Therefore, the system is marginally stable because we are having pure imaginary roots. Okay, so such systems are marginally stable. So this is how we find the value of k for the stable, unstable, and marginally stable systems, right? So again, let us solve this problem. And you can leave this. Find out how many poles are in the LHP, RHP, and on j omega axis by using Ruth table. Okay, so try to solve this problem yourself, and I have given you the answer. You can verify the answer. All right.